Okay, this video is on special functions. We've gone over, certain types of functions. There's been quadratic, radical, linear, cubic, and stuff like that. So this last piece here on functions deals with what we call special functions, and it includes a couple functions that aren't seen very often, but you do come across from time to time. And the big one here is going to be piecewise functions. So and then there's another one called step functions, which you don't see too often, but again, it's something that can't come up. So we're going to spend most time probably on the first part here, and that's piecewise functions. Piecewise functions, you can sort of figure out what it is based on the name, piecewise function. All it means is that there are pieces to a function. So, but by definition, it is a function that behaves differently depending on the domain. X values. So you might think, okay, well, what the heck? What if it doesn't come up very often? Why do we use it? And I'll tell you right now, with my financial algebra kids, they deal with piece functions a lot because when you do bills and especially cell phone bills and stuff like that, they're all based on actual piecewise functions because, like for example, if you have a 5 GB data plan. Let me zoom out here so you can see this. If you have like a 5 GB data plan, if I use 1, 2, 3, 4, 5 GB, I pay the same price. But as soon as I go over 5 GB, now I start paying a completely different price. So that is where piecewise functions come in, because you can see here that if this is a function, notice how if our input values, our domain values are between -3 and 1, it behaves a certain way, but if they're above 1, it behaves a different way. So this is why we call piecewise functions, because depending on the domain value, the function can change. So, how do we graph these? So you could do this a couple ways. I have found that the easiest way to do this is just to look at your table on a graph. So you always want to look at these endpoints of your domain, and there's where you want to start. So I'm going to first plug in this first equation into my graphing calculator, so -2x plus 1. So on my graphing calculator, I'm going to go to y equals, and do -2x plus 1. Now the reason why we do this is because we want to look at the table to see what the values are at these endpoints. So I'm going to go to my table, which is second. I didn't mean to hit graph. Well, there's what it looks like. But second table, to look at the table. Now it says here that it goes from -3 to 1. So I want to do all the values of -3 to 1. The other thing you have to pay attention to are the inequality signs. If you remember anything from Algebra 1 about inequalities, the equal to ones have a solid dot. The less than or greater than, the ones that don't have the equal to, have an open dot. So at -3, but at 1, it'll be an open dot. So we're going to graph all of these points up until 1, making sure that at 1, I have an open dot. Okay, so I'll just move this over here so you can sort of see as we graph this. So we start at -3, and -3 is 7, so -3, and it was a closed dot. There's -3, 7. -2 is 5. -1 is 3, 0 is 1, and remember here we got to stop at 1 because our domain stops at 1, and that's -1, but it is an open dot. And all we're going to do is just connect these dots, leaving that last dot open. Okay, so that's the first one. And we just did the first one there. Now you can see here that when x is 1, so x equals 1, we have a value of 2. So this is just a single value. If x is 1, then the answer is 2. Now because it's an equal to, just like inequalities, it's an equal to, we're going to have a solid dot. So at 1, the function gives me 2. So I go to 1, and the function will give me 2, and I'm going to put a solid dot there. And then the last one is when x is greater than 1. So this is where our graphing calculator is going to come in. So I'm going to go back to y equals, clear that out, and now put the new function of x squared in there. Now we have to pay attention because this is only when x is greater than 1. So when we go to our table, we're going to start at 1, and maybe you make 1 the highest number there. That 1, because this is a greater than and not an equal to, is going to be an open dot. So at 1, the calculator gives us a value of 1. So let's move this over here. So 1, 1 gives me a value of 1. Or sorry, putting in 1 gives me a value of 1. So, but it's an open dot because it was greater than and not an equal to. 2, so we're going to keep going as long as we can fit the things, because this is just everything greater than 1 now. So 2 is 4, 3 is 9, and I think that's as far as I can go. And so I'm going to graph this coming from here, and it's sort of a curve to it because it's a parabola. And it looks like that. One thing to keep in mind, if you have dots that overlap, you should never have more than one bubbled in. It's like, notice how all 3 of these are on an x value of 1, and only one of them is actually shaded in. If you should only have one. If multiple ones are shaded in, then you did something wrong. Okay, because that makes it not a function anymore. So you have the same input value giving you 2 different. The one input value should only give 1 output value. That's why these other 2 are open circles. Okay, and that's how you graph a piecewise function. Now the last part here tells us to evaluate when f is 3. And so this is where you just have to figure out where these lie. So when f is 3, what region is this? And you can refer to the graph too. If I go to where x is 3, it's going to be on this last piece here. It's going to be on this last piece right here. So I can just plug in 3 into here. Since my input value is greater than 1, it falls into this section here. So I just put 3 in for x. 3 squared is 9. Now 1. 1 does not fall into this last one because this is everything greater than 1. 1 falls into the middle where it says when x is 1. Well, when x is 1, it said that the answer is 2. So f of 1 is 2. And then f of 0. 0 falls in here. Now you can also check it here on the graph. 0 falls in this first section, or this section right here. So 0 falls in here. I put 0 into this first function. -2 times 0 is 0, plus 1 is 1. Now what about f of -5? What it looks like here, since the first range starts at -3, and if I were to go to -5 here and look up, there's nothing there. We don't have a function. Our function is not defined for this specific domain. -5 does not occur in this function. Therefore, the value of f of -5 is actually undefined. Okay, let's try one more. Okay. Now this one only has 2. Makes it a little bit easier. I don't have to do 3 things. This one only has 2. So we have when x is less than 2, and then when x is greater than or equal to 2. So we're going to put this first function into our graphing calculator. So I'm going to go over here and to where you can see it. Go to y equals, clear that out, and put negative 2x plus 3. Now we're not really concerned about the graph. We're just really concerned about the table because we want to see the values. So this is where x is less than 2. So any of these, I can put 2 there on the bottom, less than 2. But we want to make sure we check this value right here, okay? Where x is less than 2. That's our first value. And then it's going to be an open circle. So I go in my calculator to where x is 2, and it says 2 is 1, or negative 1. So I'm going to go over here to my graph, go to 2 and to negative 1, and draw an open circle. So I can draw an open circle. And it doesn't look open, but it's open. And now I'm going to put all the values that are less than 2 because my domain is everything less than 2. So I'm going to just keep going less and less and less and less than 2. So 1 is 1. And 0 is 3. And negative 1 is 5. And negative 2 is 7, and negative 3 is 9. That's all I can fit. So this is going to go right there. There's an arrow on the end because this is everything less than negative 1, so it will keep going. We just can't fit it on our graph. And now the second part. The second part also starts at 2, but because it's an equal to, it will have a closed dot, but it's a new function now. So I have to go to y equals and input my new function. Negative 3x plus 8. And go to our table. So this is everything that's greater than or equal to 2. So I'm going to start with 2 there. Let's move it over. And at 2, remember I'll have a solid dot. So 2 is 2, it says. So I'll put 2, 2, and that's a solid dot now. And I'm going to keep going for everything greater than 2. So that's 3 is negative 1. 4 is negative 4. 5 is negative 7. And 6 is negative 10. And that's as far as I can go. Now this will keep going because it's everything less or greater than negative 2. And so those are piecewise functions. So that's what they look like. They will have chunks to them, okay, as you can see. And just like the first one, we're going to go ahead and evaluate. So 0 does fall less than 2, so I'm going to use this top function. Negative 2 times 0 plus 3 is 3. Negative 2 also falls less than 2, so it's in this first one. Negative 2 times negative 2 is 4, plus 3 is 7. 2, we got to be careful with this. 2 actually falls in the second one because this first one doesn't actually include 2. It's everything less than 2. Whereas this one is greater than or equal to 2. So it does fall in the second one, so I do need to use the second one. Negative 3 times 2 is negative 6, plus 8 is 2. And 4 is greater than 2, so it's the second one again. Negative 3 times 4 is negative 12, plus 8 is negative 4. Okay. So those are graphing piecewise functions. Okay. And you probably guessed it. The next piece now is to go backwards. So now we're going to be given the piecewise function, given the graph of the piecewise function, and we actually have to write the equation for it. So this tends to be a little bit more difficult, but we can figure it out. You're always going to have line. 99% of the time, you're just going to have lines. So they're all going to follow the format of y equals mx plus b. Okay, so all we need to do is just figure out what are the equations of these lines, and this sort of will just take us back to Algebra 1 and trying to figure out the equation of this line. So we start with a function of a piecewise function with f of x. Since there are only two pieces, I'm going to make a bracket that's sort of smaller like this, so it'll have a piece right here and a piece right here. So we first need to figure out what is the equation of this line. So there's a couple ways that we can do this. Because it doesn't actually show the y-intercept, we can't just find the slope in the y-intercept and plug it in. So we can find the slope. It looks like it crosses right here, and then you have a dot up here. So it does look like it goes up 3 over 2. So we do have a slope of 3 over 2. So I'm just going to do the work sort of down below here. So I have y equals 3 over 2 x plus b. I don't know the y-intercept. All I knew is the slope. Now you may have learned how to do this in Algebra 1, but there is a way to find the y-intercept by using another point that's on here. And we can use either one of these points. I can use this point right here, or I can use this point right here, and just plug the x and y coordinate into the x and the y here, and then just solve for b. So I'm going to use this one since it's got a 0. It's negative 3 and 0. And I'm going to put negative 3. So this is, let's draw an arrow here. Negative 3, 0. So negative 3 will go in for my x. 0 will go in for my y. So it's 3 over 2 times negative 3 plus b. Negative 3 times 3 halves is negative 4.5. If you want to multiply the fractions, it's negative 9 over 2, which is negative 4.5 plus b equals 0. And then I just add the 4.5 over. And so I get b equals 4.5. So this will be my y-intercept. So now I have the equation of the line. It's y equals 3 halves x plus 4.5. So my first function is going to be y equals, not y equals, sorry, we already have f of x. Sorry, this is the y equals. We don't need the y equals. 3 over 2 x plus 4.5. Okay, and now we just need to attach a domain. Because there's a limit here, we need to attach a domain. It looks like there's an arrow here, so it'll keep going, but it stops right here. So we look at the domain, which is the x value. In this case here is negative 1 is the x value, and it's an open circle, and it's everything that is left of that, or less than. So everything, this function is valid for everything that is less than negative 1. Okay, and it's an open circle, so it's less than. So we put a comma, and we write if x is less than negative 1. Sorry, not a lot of room here, but if x is less than negative 1. Now, the second line, this one's a little bit easier because it's just a straight line across. You can figure out the slope pretty easily, and it gives you the y-intercept. So for the second one, y equals, what's the slope of a line that goes straight across? Yeah, it's 0. So it's 0x, and the y-intercept is negative 1, so minus 1. Well, 0x is just 0 minus 1, and you get y equals negative 1. So that's the other one. I don't have to put the y equals because that's what the f of x is. So I just put negative 1. Comma, because I like to line up my commas, so it makes it sort of symmetrical as opposed to putting it over there. And now this goes from negative 1 on this way. Now this one is a solid. This one's a solid dot because it has a closed circle. So it'll be when or if x is greater than or equal to -1. And so that's how you write piecewise functions. So again, your goal is to figure out the equation of the line that will give you the functions, and then writing your domain for the specific graph. Since this goes from -1 this way, that's why it's less than -1, and it's an open circle. This one goes from -1 this way, so it's everything greater than or equal to -1. Okay, we're going to try one more, and we'll talk about absolute value and step functions. So here's another example here. We have 2, so I'm going to do f of x equals, and I'm going to leave some room just for 2 functions. Now hopefully I don't mess this one up. I don't have a lot of room over here. But what's nice about these functions is they cross the y-axis, so I don't have to figure out, I don't have to do really any math, just figure out the slope. So for the first one, again, it's, y equal, I'll do it down here, y equals, now this one gives me the slope and the y-intercept. So I can see that there's a dot there, a dot there, so my slope is clearly just 1. So 1x and a y-intercept of, and it's right there, it's 2 plus 2. So my function will be, I don't have to put the y equals, it'll just be x plus 2, comma, now since this is going left, it's going to be less than, and it's an open circle, so it's just if x is less than 0, because that's the x value, 0. Okay. The other one starts here and goes up. It does have the same slope, so my second function will be the same slope, but it starts at 0. So plus 0, or just y equals x. So the second one would just be x, and then it goes with x if x is greater than or equal to 0. And that's it. Okay. Now for the last two, these are more rare, but this next one here, absolute values are actually piecewise functions, because you have a graph that goes here and stops, and then you have a graph that goes here. Okay, so I think of absolute values. We know absolute values are V-shaped, but if you didn't know, absolute values are actually piecewise functions. The formula for the absolute value is y equals the absolute value of x. Okay, so how we write that as a piecewise function, it'll be f of x, and we're going to do the equation for this line, then the equation for this line. So it's pretty easy because everything stems from 0. So let's start with this first one. This one has a slope of -1. Okay, this slope is going down from left to right, so the slope of -1 or -x. So we think about the same formula, y equals mx plus b. This first one is going to be y equals -1x, and the y-intercept is 0. So it'll just be y is -x. The first one's -x if x is less than 0. Okay. Now it doesn't matter, one of them is going to have to be an equal to because it does have a dot there, but they're on the same dot. So it doesn't matter whether you do the open circle here or the open circle here, but one of them will have to be an equal to make sure that there's a solution at 0. The other line here is the exact opposite. Instead of going down 1, it's going up 1. So the same slope, but it's just positive. And then if x is greater than or equal to 0. And that's the piecewise function for an absolute value. The last one is what is called a step function, and you'll see why pretty quickly. By graphing this, you'll see why they call it a step function. So we have four things here. So, and it's pretty short domains. Notice the first one is 1 if x is between 0 and 1. And so these are pretty short domains. We're going to graph these. So at 0, between 0 and 1, 0, because this is in a less than or equal to, this first one will be a solid dot at 0. So at 0, it says it's 1. It's 1 if it's between these lines. So at 0, we have 1, and it's a constant, so it's just a horizontal line to 1, where this is a less than, not an equal to, so it's an open circle. This is 2 if it's between 1 and 2, so we go up a step, and we have a solid dot that's also a constant and has an open dot at the end. This one's 3 when it's between 2 and 3, so we go up a step. Solid dot because this is an equal to, and it goes to an open dot. And 4 is if between 3 and 4, so solid dot to open dot again. And you can see why they call these step functions, because they sort of look like steps. This you don't see very often at all. But piecewise functions do occur in the real world. Like I said, our financial algebra class uses them. We do bills and stuff like that, and expenses. So they do occur, and there is a need for them. But this last example is an example of a step function. Because it resembles sort of stair steps, which you could probably figure out. That is it. Thanks.